Students, a topic which we are going to discuss now is scaling and unit of measurement. Scaling and unit of measurement. My description of this topic is very brief. I will not derive all the results. I will just discuss the main results only. And when we interpret the results, the unit in which data is expressed is very important. Otherwise, if you are not familiar with the unit of measurement in which dependent and independent variables are given, there is a possibility that we will make wrong interpretations. So let us see what is meant by scaling and unit of measurement. As an example, suppose that United States gross private domestic investment, gross private domestic investment and gross domestic product GDP, gross private domestic investment or simply investment and GDP is given from 1990 to say 2005 or any time series data. US gross domestic product and US gross private domestic investment. And suppose that we regress gross private domestic investment on GDP to see how private domestic investment responds to gross domestic product. Suppose that one researcher uses data in billions of dollars. Another researcher uses data in millions of dollars. And 1 billion, as it is known to you, is equal to 1,000 million. We can use data in any units. For example, you can use data in rupees, thousands of rupees, lakhs of rupees, crores of rupees, millions, billions, as you like. So one researcher uses the data in billions of dollars, another one uses data in millions of dollars. If the data is used in billions, you can convert it into million by multiplying this with 1,000, because 1 billion is equal to 1,000 million. Now let us see what are some of the issues associated with the unit of measurement. One issue is, the question is, if one researcher is using this data, another one is using this data, one question is, will the regression line be the same in both cases? That is, can we expect that we will get the same result if the data is used in millions and also in billions? If not, the second question is, which result one should use? Which results one should, if the results are different, which result one should use. That is the second issue. And stated differently, do the units in which the regressor and regressant measured make any difference in regression results? The question is whether the unit of measurement of x and y make any difference in the regression results obtained. If so, what is the most sensible course of action? That is, what should be the best course of action to follow? Remember this, when you interpret the results, the unit of measurement is very important. The unit in which we will consider this with the examples in future, but you have the discretion to use units in millions, billions, in grams, kilos, in milliliter, and the like. So, let us consider a regression model as yi samam beta 1 hat plus beta 2 hat xi plus u hat, where yi is GPDI, xi is GDP. yi is GD, gross domestic private investment. This is GDP. Now define y star I as equal to W1 into yi and x star I as equal to W2 into xi. We define two variables, y star I and x star I, as W1 into yi, W2 as x star I as W2 into xi, where this W1 and W2 are known as scale factors. Scale factors, also called, they are constants, known as scale factors. And W2, 1 may be equal to W2, or W1 need not be equal to W2. Means data given in billions, one can be converted into millions, another can be converted into some other unit of measurement. So W1 may be equal to W2 or not. Now, as it is clear, now suppose that we have this yi and xi, now y star I and x star I, and as it is multiplied by W1 and W2, and as W1 and W2 are known as scale factors, we can say that y star and x star are rescaled values of yi and xi. Rescaled values. And if yi and xi are in billions of dollars, then what is y star I? Y star I is 1000 into yi. What is x star I? Is 1000 into xi. Now consider regressing. Y star I is equal to beta hat 1 star plus beta hat 2 star x star I plus u hat star I, where y star I is W1 yi, x star I is W2 xi, and what is u hat star I? The only quantity which is not defined, u hat star I is equal to W1 into u hat. the rescaled variables. Rescaled variables. Now, we want to establish what is known as the relationship between beta 1 hat and beta 1 star hat. Beta 2 hat, beta 2 hat star. And variance of beta 1 hat and variance of beta 1 star hat. Variance of beta 2 hat and variance of beta 2 star hat. And sigma hat square and sigma hat square star. And R square between x and y and R square between x star and y star. This is what we want to establish. Now, without a proof, let me write the relations. Without proof. Proof is not very important for our purpose, so I ignore the proof here. Now, beta hat star 2 is equal to W1 by W2 into beta 2 hat. Now you know that if W1 is equal to W2, then beta hat star 2 is equal to beta 2 hat. That is, and also variance of beta hat star 2 is equal to W1 by W2 square into variance of beta 2 hat. So if W1 is equal to W2, the weights, the unit of measurement changed from one to another, and it is same for both y and x, then the estimator beta 2 hat is same. What about variance? Variance is also same, because this will become 1 square into variance beta 2 hat. Now what about the intercept? Beta hat 1 star is equal to W1 into beta 1 hat. W1 into beta 1 hat. And variance of beta hat 1 star is equal to W1 square into variance of beta 1 hat. And standard error is root of, when we take the standard error, this becomes the root of W1 square is equal to W1. Now, when we change, multiply x and y with W1 and W2, as you can see, the intercept is multiplied by W1. That is W1 into beta 1 hat. And what is W1? As I told you, W1 is the weight of Y1. W2 is the weight of Y2, the scale factor. And as you can see, the standard error, variance is W1 square into this. But when we take the standard error of beta 1 hat star is W1 times standard error of beta 1 hat. So both the beta 1 hat star and its standard error multiplied by W1. W1. Now, that is the second result. And R square xy is equal to R square between X star and Y star. That is, whatever is the unit of measurement, R square is not affected. R square is not affected. And sigma hat star square is equal to W1 square into sigma hat square. W1 square into sigma hat square. These are the results. Then, this is the case in which W1, that is X and Y, are changed. Now suppose that X not changed. X scale is not changed. Only Y changes. X scale unchanged. Y scale changes. Now what you can see is, what is X scale? W1. This is not changed. Then, as you can see, the slope, then the intercept, and also the standard errors multiplied by W1. The slope, the intercept, and the standard errors multiplied by W1. That is, W1 is the scale factor of Y, the scale factor of X. So if X scale not changed, W2 not changed, only W1 changes. W2 not changed means it remains the same. W1 alone changes. Slope, intercept, and the standard errors multiplied by W1. If Y scale change, X scale not. Y scale, if Y scale unchanged, X changes. Then X changes by, say, W2. Then what we will see is that the slope and standard errors multiplied by 1 by W2. 1 by slope multiplied by 1 by 2, and the standard error also multiplied by 1 by 2. So remember this, if W1 is equal to W2, the slope and its standard error remain unchanged, intercept and standard error multiplied by W1. R square is not affected, this is affected, W1 square. If X is unchanged, Y only changes. As you can see, Y changes by W1, then the slope W1 into beta 2 hat, its intercept also W1 into beta 1 hat, and the standard error also changes by W1. If Y unchanged, X changes, then slope and its standard error multiplied by 1 by W2. The proofs I have ignored, and if you want to know how the slope and intercept changes when the unit of measurement scaling is changed, I suggest that you practice with an example. Initially you take the values in thousands, then the values as it is, then you convert it into thousands, and observe what happens if both X and Y are converted into thousands, that is multiplied by 1000. X alone changes, Y alone changes, and see whether these relations are correct or not. It is better to study the effect of scaling and unit of measurement using an example. And in the books of econometrics, you will see a lot of examples in which econometric models are given with the different units of measurement. In some cases, if you consider the unit of measurement unscientifically, then the interpretations will not be very meaningful. So, whenever you select the scaling factor or unit of measurement, you will be very judicious. And we will consider this issue later when we consider multiple regression model, where we will consider a few more examples. That is all about scaling and unit of measurement.